Okay. So yeah, let me start off by saying that I hope everybody did the quiz and that went smoothly. You guys can have a quiz at, every day of the lecture there'll be a quiz that night. They're worth a very small percentage of your grade in the end. I think it's like 5%. Some people were worried that they didn't take the quiz in time. I really doubt the first quiz is going to affect your final grade. I think several people just had forgotten. But if you were one of those people and it actually makes a difference in the end, you can just ping us. But remember from now on that you guys have a quiz every lecture. So today we're going to talk about convex sets and functions. I actually wanted to jump back to this example real quick because I got some interesting questions after class about it. And I think I may have been potentially a bit confusing in some things I said. So the first thing I wanted to clarify was that actually this problem does have a unique solution. So there was a question last time about whether or not the solution was unique. What I was saying was that in general, convex optimization problems don't need to have unique solutions. So we're going to see, I think it's next time, we'll see that convex optimization problems, the solution set of such an optimization problem is convex. That's just a result of kind of some of the defining properties of convexity. But it doesn't need to be a singleton. It still could be a proper convex set with more than one point. In this case, the solution is unique. It's a problem in which the solution is unique. It comes from a property called strict convexity of the squared loss term. We'll define that today, and then maybe next time or the time after, I can't remember which one, we'll talk about and prove the fact that strictly convex functions, if we're trying to minimize such a function, then there is only a unique minimizer. Okay, so the examples we are seeing here had nothing to do with non-uniqueness. There is a unique solution. These algorithms weren't converging in these number of iterations. So this is just very far from optimal. That's what we're seeing. So that's one clarification I want to make. I got some interesting questions, again, about whether or not criterion value is really the right metric here after class. So maybe in some sense, there's another metric we might consider. It's a very good point that in many statistical applications or machine learning applications, the ultimate metric we care about is probably something to do with prediction or some other modeling thing or mean squared error. So it is true that the criterion value itself is probably not it doesn't have the last word in some sense with respect to the application. But so far as we're concerned in this class, for the most part, we're just going to be caring about optimization. So for us, it is really the last word. If things aren't optimal here, then we're not interested in them necessarily. Okay, I might mention a few times throughout the semester when we talk about first-order methods, potentially again later if we talk about more advanced methods, particularly when we talk about stochastic methods, the fact that optimizing a criterion to exact optimality sometimes is not necessary in practice. Solutions that are approximate sometimes will provide us with good enough test errors in lots of statistical or machine learning applications. That's an advanced concept. That's not something that I want to kind of us to start off the course thinking about. So it's a subtlety. We'll talk about it probably when we talk about stochastic methods, right? That we might actually settle for approximate solutions. But for now, maybe keep in your mind that for de facto standards that we want to be thinking about optimality as really the criterion we care about. All right, any questions on that before we jump into today's lecture? Okay. So today's lecture is on convex sets and functions. It's one of a two-part lecture. We're talking about convexity. Next time, I think we're going to be talking about optimization problems specifically. An editorial comment, this is a bit dry, convex sets and functions. It's not the most exciting thing to learn possibly. It's super important though. So in terms of, let's say how dry the content is, this might be one of the more dry lectures, but it's a very important thing to learn. And I'll be kind of assuming throughout a lot of the lecture that you're familiar with basic things in real analysis, like I'll mention probably several times about open and closed sets, in the interior of a set, this kind of stuff. If that's not familiar to you, make sure to review some of your real analysis notes from previous courses, or we also have supplements up on the course website. for all of these topics. So not only real analysis, multivariate calculus, and basic linear algebra. So if you scroll to the bottom of the course website, I just linked a bunch of different review aids that covers this, either through video or notes. Basically they're all CMU, each created by faculty for various courses or a previous TA for this course, etc. Okay, so to recap the message from last time, why is convexity important? Simply put, it's because we can broadly understand and solve convex optimization problems. And non-convex problems, for the most part, we treat on a case-by-case basis. This isn't really fair, but I think it is a fine way to think about it, and it just, as a general dichotomy. There are classes of non-convex problems we can solve, and depending on how much time we have at the end, and for advanced topics, I might do a lecture on that. But let's say to first order, you can think about the dichotomy this way. We can pretty much understand and solve convex problems. Non-convex, if we're lucky, we can. So the convex optimization form we learned last time was this kind of standard form: minimize f subject to constraints on these functions, on x from these functions gi, and further constraints with these functions hj, these being inequality constraints, these being equality constraints. And so in fact, if I didn't tell you anything about fg or h, this is an optimization problem, but it's convex when f is convex, each of the gi are convex, and each of the hj are affine. Okay, and the special property of such an optimization problem, if we actually make it convex, is that any local minimizer is a global minimizer. We actually proved that last time at the end of the class, just following from the definitions of convexity. This guy here, this D here, I'm pretty much going to drop this from here on out, but it is formally representing the intersection of the domains of all the functions. If x is outside the domain of one of the functions, then one of these functions wouldn't even make sense to be applied to x. So it's kind of necessary to have that, just something that I'll drop notationally as we go forward. So today we'll talk about convex sets. Then we'll give lots of examples and some key properties of convex sets. And this last thing is possibly the most important thing we'll cover: operations that preserve convexity. So that the workflow that you'll have in the future is I'll ask you, is this set convex? Usually I'll ask you, is this function convex? So you'll ask yourself that question when you're looking at a problem. And you have different options for how to prove that. One is just to go from the definition. You already learned the definition. You can try to prove it's verified. Another option, which is typically, in many cases, easier, is to remember that, this function was convex. That seems similar to the function that you're looking at. So one of the examples here. And the relationship between that previous function and my current function is convexity preserving. So we're going to learn all these operations that preserve convexity. So if you can remember an example of a convex function, or some of the canonical examples, you can remember the operations that preserve convexity, then you can verify convexity of, let's say, a function you're looking at typically more easily than you can by just going from the definition. So we'll do that for convex sets, then we'll do the same for convex functions. So we learned this last time. To say it again, a convex set has the property that if I take any 2 points in the set, take the line segment between them, the line segment lies in the set. Here's an example of a set that is not convex because of the fact the line segment leaves the set here. So introducing a bit more, if we have a bunch of points, x1 through xk, we can talk about their convex combination. And that's the set of all linear combinations of these points. So theta 1 x1 plus all the way through theta k xk, where these theta i's are all non-negative and they add up to 1. So we'll call this a convex combination of the points x1 through xk. And the convex hull of a set C, another important thing to define, which we denote by conv of C, is the set of all convex combinations of elements of C. And by definition, it's always convex. Okay, or merely by construction, it's always convex. So you can visualize a convex hull. For example, if we take this set up here, okay, formally, the convex hull of a set C, it's, just based on what we just said, it's the sum of theta I xi, I equals 1 to k, such that x1 through xk are in the set C, right? And these theta i's are non-negative, and they add up to 1. So pick any set of k points for any k, really. Take their convex combination. All those points go in the convex hull. If I did that here, if you imagine taking points here, I would get everything in here, right? If I take the convex combination of, say, just these 2 points, it's the line segment joining them, so I'd get everything here. And if I did that for all sets for all subsets of points in C, I would get this object, right? This guy would be the convex hull, this shaded thing. So equivalently, another way to think about the convex hull is it's the smallest convex set containing your set. So there's a bunch of convex sets that contain this. The convex hull is the smallest convex set that contains your set. Okay, it's always convex. You can check that right from the definition. Or if you use the equivalent definition, then it's convex by definition, right? It's the smallest convex set that contains your set, so it is convex. Some examples of convex sets, trivial ones like a point is convex, a line is convex, the empty set is convex. All of Euclidean space is convex. All of these points satisfy the definition of a convex set. Important ones that are not so trivial, a norm ball is convex. So if you forget what a norm is, go back and look at your notes from real analysis or look at our supplements. The set of all x such that the norm of x is less than or equal to r for a particular fixed value r. So we call a norm ball of radius r. So for example, I could use the L2 norm here. It would be the standard Euclidean ball of radius r. That thing is convex. It's also convex for any norm. Hyperplanes. So this is the set of all x such that they satisfy one linear equation. A transpose x equals b. If x is an Rn, this hyperplane is an n-1 dimensional linear space. For any fixed A and B, this thing is convex. Half space is everything to one side of a hyperplane. So it's a set of all x for which A transpose x is less than or equal to b. It's also convex. These things you can just check straight from the definition. That's the best way to convince yourself. And an affine space, which is the set of all x that satisfy a system of linear equations, like ax equals b for a given matrix A and a vector b, also convex. Check the definition to verify. Okay. So moving on to a bit more sophisticated sets. And this guy's polyhedra are very important. We'll see them a lot as we talk about linear programming. You'll talk about them on the homework. They're a very important example of a closed convex set. So a polyhedron is the set of all x that satisfies a system of linear inequalities. Set of all x such that ax is less than or equal to b, where this inequality is interpreted component-wise, because A is a matrix, b is a vector, so we're comparing the vector ax to b by less than or equal to, I mean here, component-wise. And I'll use that same convention throughout the whole course. So if I'm ever comparing, let's say a vector with to 0 with an inequality, I mean component-wise. Or if I'm comparing two vectors with an inequality, I mean component-wise. So that's a generic form of a polyhedron. We can also have equality constraints that define a polyhedron. So why is this still a polyhedron? Somebody tell me why that's okay? Yeah.
The intersection of convex and convex.
So that's good. You told me that it's convex. You already told me that an operation preserves convexity's intersection. But I was asking why this is still a polyhedron.
Fold A and C into a single matrix and B and D into a single vector, and it will still preserve the form of AX is less than B.
Almost.
We can also we can convert it into equal.
Right. Exactly. So I can write this. Right, and this is a bunch of inequalities. I can fold this into one big matrix, fold this into one big vector, and it's still of the form matrix times x less than or equal to vector. Right, and these two together are the same as Cx equals D. So, we'll kind of revisit this point when we talk about linear programming. Like, you actually never need to have equality constraints. It's general enough just to consider inequality constraints for this same reason. Okay, so that's a polyhedron. I can also think about a polyhedron as an intersection of half spaces. So every element of X, every row of A, let me call it AI. So I can actually think about AX less than or equal to B, this thing as being equivalent to, let's say, these M half spaces, AI transpose X less than or equal to BI. That's the ith row of A, and there are M rows. So it's the intersection of M half spaces, and that's what this picture is showing. Every half space gives me everything to one side of its to a particular line in this 2D image. And if I intersect them all, I get a polyhedron. Simplex is a special, very special polyhedron that I get by taking the convex combination of k plus 1 points. So if you pick k plus 1 points, and these points satisfy a property called affine independence, which basically means that there is no lower dimensional affine space that contains them. So you should know what linear independence is. That should be familiar from linear algebra. For affine independence, I would say you can just take a look at the review that we wrote if you're not sure what that means. But it's a slightly different notion of linear independence. If we take, let's say, k plus 1 points, and we take their convex combination, then that's a simplex. It's a very special case of a polyhedron. And the example you'll all probably remember is the probability simplex. It's what happens when I take the convex combination of the n standard basis vectors. So this guy, E1, is 1, then all zeros. E2 is 0, then 1, then all zeros. And EI is all zeros except for a 1 in the ith spot. If I take the convex combination of these n guys in Rn, then I get this set. It's the set of all vectors that are non-negative and add up to 1. We call it the probability simplex often, because you can think about the entries of W as defining a probability distribution. Okay, cones. We won't focus on them as much in this course, but we will talk a bit about conic programming in 2 lectures. And conic programming, in some sense, is very, very, very general. So it's a very large class of problems, which we'll emphasize in 2 lectures. And a lot of software actually converts things to conic programs. So they are very important at some level. And it all starts with an understanding of cones. A cone is basically a set that satisfies a very simple property, which is that if I take any point in the set and I look at the ray passing through that point, so it's a set of all tx such that t is non-negative, then that ray has to lie in the set. Okay, so the set a cone has to contain 0 because I can take t equals 0 here, and I would see that 0 has to be in the set. A convex cone is a cone that's also convex. So if you combine this property with the convexity property, you'll see that actually what we require is that if I take t1 x1 plus t2 x2 for any x1 and x2 in the set, and for any t1 and t2 that are not negative, that has to lie in the set as well. That's called a conic combination, this thing right here. So let me pause and ask, is every cone convex? Did I have to say that? Did I have to even kind of separate this out? Is every cone convex? No. So what's an example of a cone that's not convex?
Ice cream cone.
An ice cream cone. Okay. So then, yeah, I mean, I don't know how well I can draw that. I'll draw a simpler example, which I think is in line with yours. Say this is 0. Say this is x1. Say this is x2. And if I just take the ray going through x1 and the ray going through x2, then this thing is a cone. But it's not convex, right? Because if I take x1, I contain its ray. If I take x2, I contain its ray. But it's not convex, clearly. So I think your example is just a higher dimensional version of this. Right, so convex cones, exclude this possibility, obviously. They're also convex. And we can talk about something called a conic combination of points, which is now a linear combination of points x1 through xk where all of these are non-negative. So we don't constrain them to add up to 1. We just constrain them to be non-negative. In the conic hull of a set, just like the convex hull, the analog for conic combinations, the conic hull just collects all conic combinations of points. And so by construction, it is a cone. So if I take a set, I take, for example, the conic hull of this set, I would get, well, this already is a cone, actually. So I would just get the set itself. But I just had, if the set was just 0, x1, and x2, so if it was a discrete set with 3 elements, this would be the conic hull. No, actually, that's not true. The conic hull would be this guy. Right, because I'm allowed to take theta 1 x1 plus theta 2 x2. So I'm allowed to get things in the middle as well. Okay, so some examples of convex cones. A very important class of cones, obviously the one we'll care about. So if you look at the set of all x comma t such that the norm of x is less than or equal to t, so it's actually not a norm ball now because t is a variable that defines the set, then this is a cone for any norm. So let's suppose x is n-dimensional, t is here, it's non-negative real, then this set is n plus 1 dimensional, set of all xt that satisfy norm of x less than or equal to t. That's a cone. It's a convex cone, something that you can prove right from the definition. And if we take the L2 norm, then we get something called the second order cone. So I've actually also heard this called the ice cream cone, which is why I was slightly confused about the last example. But if I take this is supposed to be now me drawing in 3 dimensions. If I take x1, x2, and if this axis is the t-axis, then the set of all x comma t such that the norm of x is less than or equal to t, right? This set xt, this is going to be now 3-dimensional, such that the norm of x, the L2 norm here, is less than or equal to t. It's going to look like this. So it'll extend infinitely, but it'll look like this. Sometimes this is called the ice cream cone, but it's also called second order cone. Okay, another important convex cone is the normal cone. We're going to actually see this pop up when we talk about subgradients quite a bit. So if you give me any set C, doesn't have to be convex, just any set C, and any point x that's in the set C, the normal cone of the set C at the point x, which we write as n subscript c of x, it's a set of all vectors g such that the inner product of x and g is biggest among all points in the set. So if I take the inner product of g with all points in the set, it's biggest at x. So g transpose x is bigger than or equal to g transpose y for all y in the set C. I drew some examples of normal cones that kind of protrude out from the set. They're actually translated normal cones. But we will revisit the normal cone, I think, in detail once we talk about subgradients. But an important property, again, something you can check from the definition. Every time I say that, if you don't believe me, or maybe even just for practice, I would suggest that you just write down the definition and check it. It doesn't take longer than a minute. This is always a convex cone regardless of C. So even if C was a really weird set, you always get a convex cone for its normal cone. Okay, last thing is the PSD cone, infinite cone. Our first example of actually moving outside of Euclidean space to the set of symmetric n by n matrices. So this is how I denote the set of symmetric n by n matrices, Sn. Very important class that we'll talk about because we will talk about semi-definite programming later in the course. Actually, even in 2 lectures, I'll tell you what an SDP is. So the positive semi-definite cone is a set of all symmetric n by n matrices that have the property that the lowest eigenvalue is non-negative. Okay? So this means x, the smallest eigenvalue of x, is non-negative. Anytime I write, yeah, I mean that's one definition. An equivalent definition, just to remind you, is probably something that if you haven't taken linear algebra in a while, you might be rusty, but again, we'll go through all of this on the website, so I would definitely take a look at that if what I'm about to say does not seem familiar. This means that the smallest eigenvalue of x, which sometimes we'll denote by lambda min of x, is not negative. It equivalently means that A transpose XA is non-negative for all A. Two equivalent definitions for positive semi-definiteness. Okay. Just a note in notation, anytime I write something like, for example, A curly bigger than or equal to B, I mean by that that A minus B is positive semi-definite. Okay, so it means A minus B has a smallest eigenvalue that's bigger than or equal to 0, or this property holds for x equals A minus B. So this is how we define an ordering on symmetric n by n matrices. By any time we write something like this, we really just mean that their difference is PSD. Okay, so the set of all PSD matrices is a convex cone. Why don't we check that one? I've been telling you that you can check everything from the definition. Let's just check that one, okay? As an example. So let's take the set S n plus, set of all x I want to check it's a convex cone. I can just remember the definition. So let's suppose I have x and y that are symmetric n by n matrices that are also positive semi-definite. And now I want to take, as an example, t1x plus t2y for any non-negative t1 and t2. And I want to check if this is PSD. So if that's true, then I will have checked that the positive semi-definite cone is a convex cone. I mean, this matrix is clearly symmetric. If these were symmetric to begin with, this is definitely going to be symmetric. So that part does not need to be checked. So how do I check this? Well, the easiest way is actually not to think about the smallest eigenvalue. It's just to look at the second equivalent definition of positive semi-definiteness, which is this one. So I'll just take any A, and I'll take A transpose t1x plus t2y times A. Right? This is equal to t1 times the quantity A transpose xa plus t2 times the quantity A transpose ya. I just move the a's in through this sum. I factored out these constants t1 and t2. This is non-negative. That's non-negative. And actually t1 and t2 are also non-negative, right? By choice here. So this whole thing is non-negative. So that we've checked this property. So it's therefore a convex cone. Okay, I just want to do one example when I keep claiming that it falls from the definition. The rest of the examples that I claimed were convex or convex cones are about, this, they require this level of argument. So it's really just right from the definition. Okay, so moving into some more interesting stuff. What are some key properties of convex sets? I would say the key property of convex sets is what we call the separating hyperplane theorem. And it is as follows. If you give me any two disjoint convex sets, so two convex sets that don't have an intersection, then there is a hyperplane that separates them, which means that there is an A and a B, such that if I look at the set of all x for which A transpose x is bigger than or equal to B, that contains one of my sets. and if I look at all the set of all x such that A transpose X is less than or equal to B, that contains my other set. Okay, I don't know how well you can see this picture, so I'll just kind of recreate it much bigger. So I have two convex sets, C and D. This, let's say to this side of the half space, is the set of all x for which A transpose X is, I'll be consistent with in that picture, less than or equal to B. This one is bigger than or equal to B. Okay, if they're convex, they have to be separated by a hyperplane. So that is a fundamental property of convex sets. And for a proof, actually, you can look at Boyd and Vandenberg. I think they give a proof for a fairly general case in the text, just from first principles. Basically, the proof is find 2 points that are closest, look at the line segment that joins them, and define this affine space to be orthogonal to this line. And that'll do it. That'll separate them based on the notion of convexity. So a couple caveats that are important to mention. What about strict separation? Or not caveats, these are variants. What about strict separation? Do you guys think strict separation is always possible if I give you two disjoint convex sets? By that I mean I have to have A transpose X is strictly larger than B, and A transpose X is strictly smaller than B. Who thinks that's, I see some people shaking heads. So why is that not possible? What's an example for which, yeah?
You had two rectangles, but one of them was like, and they were almost overlapped on, if they were touching.
Okay, so I think, yeah, I think as we, let's take an example, we could take the set of all x, y, such that, let's say, y is positive, and the set of all x, y, such that y is less than or equal to 0. So this is like a closed half space. This is an open half space. They're both convex. Nothing strictly separates them, because if I take this, right, if I try to take as an example the x-axis, seems like the only half space that I could separate, or the hyperplane that could separate them, it cannot strictly separate because this thing includes 0. So that's a fine example. What happens, though, if I told you that both C and D were closed? So your example is one in which one of the sets is open. Closed convex sets, do we get strict separation? So the answer is no. It's actually, it probably will take you a couple minutes to figure out a counterexample. So if I can tear this page off, I will give it to you now. Hint, hint, this may or may not be on the quiz. Let's consider the following two sets. So I'll take, again, the set of all x, y, such that y is less than or equal to 0. That'll be this set. It's closed and convex. I'm also going to take the epigraph, let's say, of 1 over x. Let's say it's a set of all x, y. Didn't define the epigraph yet, did I? I did not, sorry. So I'll just write it down then, such that y is bigger than or equal to 1 over x, and x is bigger than or equal to 0. Okay, it'll look like this. It should be asymptoting here. Okay, so each of these is closed and convex, but there's no hyperplane that strictly separates them. This thing is going to get arbitrarily close to 0, right? This set here. So there's nothing, the only candidate would be the x-axis, and again, I don't get strict separation. So strict separation requires actually one of the sets to be bounded, and then you get strict separation, and that's something you'll prove in the homework. So this is a nice counterexample to have in mind as to why generally you cannot expect they'll be strictly separated. Supporting hyperplane theorem is actually very related to the separating hyperplane theorem. In fact, the proof of this just uses a separating hyperplane theorem. The proof of this is very short, and it just applies the separating hyperplane theorem. And it is as follows. If you give me a convex set, and any point on the boundary of that set, so if you forget what that means formally, then go look at the real analysis review. Give me a point in the boundary. Then there's a supporting hyperplane passing through it. And what that means, I guess I wrote it down here and formally, so I won't write it on the piece of paper, that I have some A such that A transpose X is less than or equal to A transpose X0 for all points X in the set. Okay, so the inner product with this vector A is maximal, and actually everything in the set lies less than or equal to A transpose X0 for some A. Okay, so that's the definition of a supporting hyperplane. And this is a very important property because, in fact, it's what we use to prove existence of subgradients of convex functions. Just an application of the supporting hyperplane theorem. So both of these theorems that I just told you actually have partial converses. So this is why I say that there's such central properties of convex sets, is because in a certain sense, if sets satisfy these, and you add like this type of existence of a supporting hyperplane, and you add a bit more conditions, then it must be convex. Or if you have two sets that have a hyperplane that separates them, and one of them is open, then they must be convex. So actually, these are converses. If you want to see details, you can check section 2.5 of Boyd and Vandenberg. I'm going to try to make it, let's see how much more we have. Yeah, I'm going to try to make it to functions, then we'll take our break. So we only have a bit more before we get to functions. So operations that preserve convexity. And this is, as I said, going to help us out when we go to prove convexity of given sets in the future. I just told you a bunch of sets that were convex. All of these things, and all of these things, etc. And now I'm going to give you operations that preserve convexity. So you can use these to prove that a bunch more sets are convex that you might encounter. So the intersection of two convex sets is convex. Something you can prove right from the definition. If you scale and or translate a set, then it's convex. So this means multiplying a set by a scalar. So every element in the set by a scalar. Or adding every element in the set to a vector. So if I write A times the set C plus B, I mean the set of all AX plus B for points X in the set C. That's convex if C was convex in the first place. This one is super useful. If I take an affine image or an affine pre-image of a set, it's still convex. So let's start off with the image. If you give me an affine function, which means f of x is equal to a matrix A times x plus b, that's what we call an affine function. So in this class, we'll distinguish between affine and linear, just because it's helpful sometimes. Linear would mean that it's just ax. If I'm adding a constant to it, it's called affine. So that's an affine function. If I apply this affine function to every element in the set C, which I denote by f of c, so it's the set of all f of x such that x is in C, it's called the affine image, or the image under f of the set C. That thing is convex if C was convex to begin with. Another thing that just follows very directly from the definition. A kind of counter to that, or maybe the opposite in some sense to that, is applying an affine preimage. So when I write f inverse of a set, I don't mean that this function f in general is invertible. This doesn't mean the inverse of f if I'm applying it to a set. This means the preimage, or the inverse image, of the set D under the map f. And that is the set defined as the set of all x for which f of x is in the set D. Okay, so if f had an inverse, if f inverse existed, this would just be the image of D under f inverse. But in general, we can always write this, and this would always make sense. It's just a set of all x such that f of x is in D. So that's called a preimage, and if f is affine, it's called an affine preimage, and that is also convex if D is convex. So two very useful properties, especially because we'll see a similar thing with convex functions, and it'll save you a big headache. Basically, you will not have to use the chain rule in some sense to prove convexity if you remember that you can compose things with affine functions. Okay, so for sets, it's just useful, let's say, from first principles. All right. And in the homework, you'll be I think actually I'm going to have you prove that these are both convex. So I was, going to maybe do one here, but I remembered actually it's on the homework. So this is something that you'll prove is convex in the homework. It's fairly straightforward. So as an example, a couple examples before we go to the break. It's like an inequality, but actually involving matrices. We call it a linear matrix inequality. So if you give me any matrices, A1 through AK and B, each of which is symmetric and n by n, we say that a set of this form, the set of all x such that the first component of x times A1 plus the second component of x times A2, etc., plus xk, ak is less than or equal to b. This is called a linear matrix inequality. Okay, and the set of all x satisfying this inequality is convex, regardless of these matrices A and B. So just to remind you, by this, if I write down this thing, as I had said a little earlier, by that I mean that B minus, x1, a1 minus xk, ak is positive semi-definite. Okay, and it makes sense to multiply a matrix by a scalar. I just mean I multiply every element of this matrix by that scalar. That's what I mean by x1, a1 as an example. So this is called a linear matrix inequality. One kind of neat thing about this is that it's always convex regardless of these matrices. It's a convex set in X. So it's in RK, and it's a convex set in X. We'll see these things pop up all the time when we talk about semi-definite programs. So this kind of constraint on X is a convex set. And there's two ways to prove that it's convex. Okay, and the first way is to check the definition of convexity, which I will not go through and let you do. Okay, just check that if you have any one point in the set, any second point in the set, that the line segment between those 2 points lies in the set. That's this way. The second way is just to notice that, this is an affine preimage of the PSD cone. Okay, so if I look at the set of all, let's say let's say matrices Y, such that Y is positive semi-definite. That's the PSD cone. It's a convex cone. And if I define f of x to be the function b minus the sum of xi ai, and if I look at the set f inverse, remember our notation for this thing was S n plus. I look at the preimage of this set under this map. That is exactly our set. It's a set of all x such that f of x is in the PSD cone. Right, which means the set of all x such that b minus the sum of ai, or xi ai, is PSD. That's our set. So it's just a preimage of the PSD cone under linear map. Therefore, it's convex. So an example of how we might save ourselves from having to do something from the definition that maybe not in this case, but in many cases would require more work. So a few more operations that preserve convexity, and then I'll take the break. I think I'll skip this second example. And you'll see something like the first thing come up as a bonus in the homework. It's not on the homework itself, it's just a bonus question. Perspective images and preimages. So the perspective function basically takes two arguments. Okay, one block being a vector, so like x is an Rn, and z is a positive real number, and it returns x divided by z element-wise. So this is an dimensional vector with every element of x divided by z. And z is restricted to be positive in this map. Otherwise, well, if it's 0, this doesn't make sense. And if it's allowed to be negative, then we don't get something that's going to preserve convexity. So the domain of z is r++. This denotes the positive reals for us. If you apply this perspective transform to a set, so it means you just take every element of the set. Let's say xz is an element of the set, and you apply the perspective transform to it. That's an element now of P of C. Then this is convex. So P of C is convex if C is convex. And preimages under this particular function, the perspective transform, also preserve convexity. So there's some physical interpretation of what perspective functions do in terms of, it's called looking at an object through a pinhole camera. You can check Boyd and Vandenberg for that. It ends up, this can be quite useful in certain contexts, and the homework bonus gives you an example of that. The last thing that we'll talk about is a perspective function composed with a linear function. So it's called a linear fractional transform. So it's of the form ax plus b, where a is a matrix here and b is a vector, divided by cx plus d, where this whole thing in the denominator is a scalar. So if we restrict this function, the domain of this function, to be x for which this is positive, c transpose x plus d is positive, then this is called a linear fractional function. This somewhat remarkably preserves convexity, and so does its inverse image. So this is an example where if you happen to recognize that a set was an image of a basic convex set under this linear fractional transform, that actually would probably save you a lot of grunge work trying to prove that it was convex in the definition. Right, this is a fairly complicated transform, and it still preserves convexity, and so does its preimage. And I have an example of where you'd use that in the next slide, but just for the sake of time, I think we're going to skip it. All right, let's take a break, and we'll come back and do the same for functions. Just have basically, we're going to go through the same game with functions. Again, a bit dry, but trust me, you'll be empowered after this lecture to go and recognize convexity wherever you are, which is a pretty cool skill to have. So convex functions, just to remind you the definition, they have really one key property, and one property that we tend to kind of forget, but we think of as a precursor. And let's say the precursor is that the domain must be a convex set. So we can't have a function whose domain is non-convex. Okay, given that's the case, this is really the key property, is that f of, let's say, tx plus 1 minus ty must be less than or equal to tf of x plus 1 minus tf of y for all t between 0 and 1 and for all points x and y that are in the domain of our function. So graphically, the line segment joining f of x and f of y lies above the function. So concave function is the opposite. So it's a function for which the opposite inequality must hold. This must be greater than or equal to the right-hand side. And one thing that you'll see is that f being concave is equivalent to minus f being convex. So basically, I'm just going to tell you about convex functions. If you want to know about concave functions, apply everything that we say to minus f. It'll give you statements for concave functions. So here are some very important modifiers. Strict convexity. Strictly convex means that this inequality is strict as long as t is between 0 and 1. Not equal to 0 or equal to 1, but strictly between 0 and 1. So in other words, the function f lies strictly below the line segment everywhere in between 0 and 1. It's obviously going to meet the line segment at 0 and 1, but it has to lie strictly below the line segment. So the way I think about strict convexity in my mind is that f is at least as curved as a linear function. So linear functions are not strictly convex. Linear functions are convex. something I guess we will state in a few slides, but maybe should just be kind of intuitive to you, right? A linear function is convex. If I take any 2 points, look at the line segment joining them, it's equal to the function. Okay, so it meets the definition. They're not strictly convex. Okay, because for strictly convex, the function has to lie strictly below the line segment joining 2 points. So the way I think of strictly convex is that it's like I guess maybe verbally I said at least as much curvature. That's not what I meant. It has more curvature than a linear function. So it's actually curved compared to a linear function. Somehow what this inequality means, at least intuitively. Strongly convex is another important modifier, and it's an even stronger condition than strict convexity. So that's how you can remember it. It means that if I were to subtract off a quadratic function from f, it's still convex. So here m is a parameter, so we say that f is strongly convex with the parameter m. It's a positive number. And this is the 2 norm of x squared, so it's the sum of xi squared. And if I can subtract off this quadratic function from f and it's still convex, then we call it strongly convex. Sometimes we say it's m strongly convex to emphasize that this parameter m. And the way I think about that, try to remember, is that it's actually at least as convex as a quadratic function. So there are functions that are more curved than linear functions, but less curved than quadratic functions, right? So those functions would be strictly convex, but they wouldn't be strongly convex. If the function is actually at least as curvy as a quadratic function, then it's strongly convex. It's a way to remember it. So strongly convex is the strongest condition. It implies strict convexity. That implies convexity. Right? So we just kind of gave examples, at least informally, of things that are in one class but not in the other. And everything here is analogous for concave functions. So I can say strictly concave or strongly concave. You can formally get the definitions by applying it to minus f. But you can also think that maybe for strict concavity, I need a strict bigger than or equal to there. Okay, so both very important things to know. So what are some examples of convex functions? Well, a ton of univariate functions are convex. You can probably think of way more just by drawing them. The exponential function is convex, right? This, again, it should just make intuitive sense to you. This kind of thing is convex. Power function is convex. If I take x to some power that's bigger than or equal to 1, that's convex. If I take x to the power of a half, it's not convex. It's in fact concave, right? Again, it should be intuitively obvious just from drawing these things. Log is a concave function whose domain is the positive reals. Okay. An affine function, so now we're talking about functions on n dimensions. It's both convex and it's concave. In fact, it's the only function that's both convex and concave. If you have that f is both less than or equal to the right-hand side and bigger than or equal to the right-hand side, then it must equal the right-hand side. And that means that f is it satisfies this linear equality. It means that only these functions can satisfy such equalities. A quadratic function, we'll see this a lot. It's convex, provided that this matrix Q here that defines the quadratic is positive semi-definite. So, all of its eigenvalues are non-negative. So that's an important qualifier. If Q has a negative eigenvalue, it's no longer a convex function. And, a function that's our friend from doing, let's say, regression is the least squares loss. So if I look at the 2 norm of y minus a matrix A times x squared, this is the kind of thing we would minimize if we're doing regression, where the response is A and the response is y and the variables are A. This is always going to be convex. Why? If you expand this, it looks like a quadratic of this form. And Q in that expansion is A transpose A. A transpose A is always PSD. How do you see that? If you've forgotten maybe some things from your linear algebra courses, as an example, I can just take any vector b, and I look at b times A transpose A times b, then this is always going to be non-negative. Why? It's because this thing is equal to A times b. This thing is equal to, let's say, z transpose z. So it's the sum of zi squared, where z is equal to ax, or ab. So clearly this can only be bigger than or equal to 0. So then that thing is positive semi-definite. So this our friendly loss, the least squares loss, is always convex. Doesn't matter what A is. Any norm is a convex function, an important class of functions. So some examples of norms on vectors are the LP norms. So the 2 norm you're familiar with. It's just the Euclidean norm. The sum of xi squared, take the square root. The P norm is more generally defined as the sum of xi to the p, and then once you take that sum, you take the 1 over pth power of that to define the norm. That is, this thing is a norm, which means it satisfies 3 properties. In case you've forgotten what norms are, take a look at the review notes. But basically, it's 0 if and only if x is equal to 0. It satisfies that the norm of a times x for, let's say, a positive a is a times the norm of x. It's called positive homogeneity. And the third thing it satisfies is the triangle inequality. The norm of x plus y is less than or equal to the norm of x plus the norm of y. So those 3 things define a norm. And it turns out that actually those 3 things are good enough to imply convexity. So any norm is convex. You just prove that from the properties of a norm. And this is an important class of norms, LP norms. And when P is infinite, we define it to be the maximum absolute entry of x. So the 3 most common LP norms, I saw the question, Nick, I'll get to it in just a second, is 1, 2, and infinity. So these are the 3 most common cases. We're going to talk about the L1 norm a bunch because it's sparsity inducing when we use it in optimization problems as a penalty. So we'll talk about the lasso and that kind of stuff. 2 norm is, of course, ubiquitous because of, we use it to measure distances in Euclidean space. And the infinity norm is also very useful. It's just the maximum absolute entry of a vector. There's a question there. Yeah. Good question / comment. We're only considering P being bigger than or equal to 1. So when P is 0, we kind of talk about the L0 norm. And we really should be using norm in quotation marks, but we never do. And we usually define this as it's the number of non-zero entries in X. So the sum of indicators that xi is not equal to 0. It's not actually a norm because it doesn't satisfy positive homogeneity. If I take the norm of a times x for a positive a, it doesn't change, in fact, the norm at all. Right? It's just a number of non-zeros. So it's not a norm. It's not convex. Not our friend for now. Let's say that. But it is very interesting. It's elusive. So yeah, good. That's a good kind of related point. Any other questions? Okay, norms on matrices. So we're going to talk about matrices here and there. We talked about already like an important cone of matrices, which is the PST cone. We'll talk about semi-definite programs and so on. So we'll be using matrices quite a bit. What are some norms on matrices? Well, 2 of the most common norms are the operator norm and the trace norm. So again, maybe like scratching off all the rust from previous courses, you should remember what the singular value decomposition is. So if I take the SVD of x and look at its singular values, so x doesn't have to be square here, it can be rectangular. If I take the SVD of x and look at its singular values, if I look at its biggest singular value and actually define the operator norm to be equal to that thing is a norm. So it has all the properties of a norm. If I also look at the sum of its singular values, it's also a norm. And we call this one the trace norm. There are other names you might hear these go by in the literature, like sometimes this is called a nuclear norm. Sometimes this is called the 2 norm for matrices. But yeah, we're going to call them in the trace. And they are both norms, therefore they are both convex. Biggest singular value is sum of singular values. Let's see how much we have left. We have a little bit left. So some more examples of convex functions, indicators. So one that we'll use a lot. An indicator function is defined as 0 on the set C and infinite outside the set C. I'm going to write it as I sub C of x. This thing is going to be a convex function, provided that C is convex. Okay, this thing is, let's do another example of checking convexity. So we have f of x equal to I C of x. What are the 2 properties I need to check for convexity? The first is that the domain of the function is convex. The domain here is actually C, because it's only finite on C. It's infinite outside of C. So that's convex by assumption. And now I have to take any 2 points in the domain. Right, I have to take any 2 points in the domain, x, y in the domain. And I have to check that f of x, f of tx plus 1 minus ty is less than or equal to t times f of x plus 1 minus t times f of y. Well, that's 0 because it's in the set. That's 0 because y is in the set. This whole side is 0. This thing is in the set by convexity, right, of C. So this whole thing is 0. That's, in fact, all I have to check. I don't have to check what happens if, say, y is outside the set, right, because I only have to check this for the domain. So very, very straightforward one to check. But it's not going to be convex if C is not convex. Okay. And you can see why that's true, because if C wasn't convex, well, first of all, this would break, but also I could make this infinite somehow by leaving the set. Right? The left-hand side could be made infinite. The support function, which I'm actually writing in a way that suggests it's related to the indicator, which we'll see much later in the class, I star of C, is actually the maximum inner product I can make with x out of any point in C. So it's the biggest x transpose y, such that y is in the set C. That's always a convex function, regardless of whether C is convex or not. Something that you guys should check from the definition. It's kind of interesting that we don't have to worry about convexity for support functions. And the max function, but let's take, for example, the max of x1 through xn, it's also convex, also follows from the definition. So what are some key properties of convex functions? There are actually more than we learned for convex sets. There are several key properties. And there's one actually that relates convex functions to convex sets. And that is maybe what we'll start off with. It's called the epigraph characterization. So first of all, the epigraph of a function is pictorially everything that lies above the function. So if I have any function like this, hopefully by now, or at least if not now, then very soon, you'll recognize that that's not convex. It does all sorts of weird things. Its epigraph is everything above the function, so it's this set. Okay, and formally it's the set of all x comma t, for which x is in the domain of f, such that f of x is less than or equal to t. Right, so that's like here, if I call t y, this is like y is bigger than or equal to f of x. It's this whole set. So this set is convex if and only if my function is a convex function. It's a very important property that connects convex sets and functions. And in fact, it really is through this characterization that we can learn and prove everything about convex functions. If all you knew was convex sets and you wanted to understand things about functions, because of this equivalence between convexity of functions and sets, you can actually get everything for functions just from sets. and plus a lot of geometry, but still it really makes convex sets more fundamental in some sense. So that's called the epigraph characterization. The equivalent should make sense to you from seeing pictures like this. Another property of convex functions is that it's a convex function if and only if it's convex on every line segment. So if I just take a line through its domain and I look at how the function acts on that line, if that univariate function is convex for every line, then the function is itself convex. This is actually a useful property in proving that some functions are convex that are kind of quite complicated. You can reduce them to an arbitrary univariate function by looking at a particular line, and then you can use maybe more simple characterizations. I think, for example, proving that the log determinant of a matrix X is convex follows, basically uses this characterization, that I'm going to restrict that function to every line segment, and then look at the convexity in this univariate space. Okay, here's a one-directional property. If a function is convex, then its sublevel sets are convex. So this is the set of all x for a fixed t, such that x is less than or equal to t. So draw a picture for you. If I have a function like this, convex functions in 2D kind of always either look flat or like quadratics. We can't really do much in terms of creativity. If I have a convex function and I look at the sublevel set at a level t, so I just pick some t and I look at the set of all x for which f of x is less than or equal to t, that's actually going to be this set right here. Okay, it's called a sublevel set at level t. So for a convex function, all these sets are convex for any t. How about the converse? If I gave you a function with this property, that all of these sets are convex, is it a convex function? No, it's not true. Yes, I think I heard wavy parabola, which I'll interpret like this. So that guy has convex sublevel sets, but it's not convex. So functions that actually satisfy this property, they're called quasi-convex. It's a weaker property than convexity. All right, we're running a little behind. Actually, yeah, we are. We're running a little behind. I thought for some reason I only had examples after this. I wanted to get through a few more things. So there are two characterizations of convexity that have to do with first and second derivatives. These things are very important because they often are used for checking convexity. The first order characterization is as follows. If f is differentiable, okay, then it's convex if and only if it lies above its tangent line everywhere at any point. So this is the tangent line to the function at the point x. F of x plus the gradient of f, inner product with y minus x. This defines a line in y. And if f of y is above this everywhere, then the function is convex. The picture is like this. Here's the point x. I look at the tangent line. That's actually this thing here on the left-hand side. If f of x is above this everywhere, then it's a convex function. It's a first-order characterization. The second-order characterization is as follows. If f has two derivatives, then it's convex if and only if the Hessian, this is now a matrix, it has all the partial derivatives. So for example, in the ijth component of this matrix, it's the derivative with respect to xi and xj of f. So if that matrix is positive semi-definite for all x, then my original function is convex. So on the quiz today, I believe I ask you whether or not a function is strictly convex if and only if the Hessian is strictly positive definite. So it has a strictly positive smallest eigenvalue. And let's just even reduce that to a one-dimensional example. Is a function convex if and only if its second derivative is positive? Strictly convex if and only if its second derivative is positive. What do you guys think? Yeah, I might have guessed yes also if I had seen that for the first time. It seems like probably, but it's a trick. The answer is no. And here's the example, x to the fourth. X to the fourth is strictly convex. It's actually more curved than a quadratic, but it has a 0 derivative at 0. So if I take the 0 second derivative at 0, if I take its second derivative, then it's going to be, what is that, 4 times 3 times x squared. And that's going to be 0 at 0. So it doesn't have a strictly positive second derivative, yet it is strictly convex. So it's something people often mix up. Second order characterization is an equivalence for convexity, but it's not an equivalence for strict convexity. If this is strictly positive, then it implies strict convexity, but not the other way around. We can have strictly convex functions that don't have strictly positive second derivatives or strictly positive definite Hessians, this being an example. Okay, Jensen's inequality, let's just skip that for the sake of time, but it's there, and it's something you guys know from, hopefully, from statistics. Okay, so let's just say a nice example of a convex function that's quite complicated is what we call the log sum x function or the softmax function. The proof of convexity is on this slide. So I'm not going to be able to go through it because of the sake of time, but it is a convex function, and the proof is on this slide. And what we use, somehow this example appeared too early. We actually use operations that preserve convexity. So this is the thing I wanted to us to get to, and if we don't get to all of them, then we'll just pick up next time by completing the operations that preserve convexity. So if I take any combination of linear combination of convex functions that have positive weights or non-negative weights, then that thing is still convex. Non-negativity is very important here because if I just flip the sign of one function, it becomes concave if it was convex to begin with. So it has to be a non-negative linear combination. Okay, pointwise max and pointwise min. Two nice transformations that we'll kind of run into a lot. They both preserve convexity, but one does so more generally. So if I have a function, let's say f, that's indexed by s, and s is really any parameter. Could be in a discrete set, could be in a continuous set. You know, this s could be like Euclidean space. This s could be like a discrete set of integers. This s could be like, you know, a finite set. So I have some functions indexed by s, and I take at every x I take the maximum of f of x over all these functions f in my collection. Then that thing is always convex, provided that each one of these functions was convex to begin with. So we call this pointwise maximization. And the set S here is really arbitrary. Like I said, it can be infinite. It could even be uncountable. It could be itself Euclidean space. So doing pointwise maximization preserves convexity. So doing kind of pointwise, or we also call it partial minimization, preserves convexity, but only for under stronger conditions. So we write things slightly differently because now I actually have to think about g, my functions, as being a function of x and y together, so I'm no longer subscripting them, because it's important to think about it as a joint function of x and y. And this has to be jointly convex in x and y together. It's not that for every fixed y this has to be convex in x, which is what we kind of assumed up here. It has to be jointly convex in x and y. And if the set of all y over which I'm taking the minimum is convex, so this set C is convex, then this operation preserves convexity. I get out a convex function of x if I minimize out y over the set C. So in short, maximization basically preserves convexity whenever the functions you're maximizing over are convex. Minimization only preserves convexity under stronger conditions in which the function I have to think about as being a function of two blocks of variables. It's convex in both variables, and the minimizing set for one variable is convex. So it requires us kind of to assume a lot more. And one nice example, I guess we'll just quit after this example and pick up the rest next time. is distances to a set. So I'll just state this example, and then it'll be on the quiz, so you'll be forced to think about it as well through that. But if I think about the maximum distance or the minimum distance to a set, okay, defined as follows. If I have a set C, and I define, let's say, the max distance to the set C, it's the maximum over all y of the norm of x minus y, where x is my point that I've kind of fixed here ahead of time, and y I'm looking at all points in the set. This thing is convex for any fixed y, regardless of whether or not C was convex to begin with. So that's, I think, kind of an amazing fact. The maximum distance to any set C, even if C is some very weird, pathologically non-convex set, is a convex function. Why? It's because for every fixed y, this function, norm of x minus y, is convex. That's all we needed according to our pointwise max rule. Fixed y, just consider that inside function as a function of x, it's convex. Minimum distance is a different story. If we want to talk about the minimum distance to a set C, then we need the set that we're talking about to be convex in the first place. So for that function to be convex. So the summary is that, minimum distance to a set is a convex function only when C is convex to begin with. Max distance to a set is always convex. And these are just applications of these rules, pointwise min and partial maximization. Okay, so we ran out of time. I think we only have basically composition rules to talk about next time. I don't think you're being quizzed on that, so you should be all good. And I will see you guys on Monday.